torque. So when a force causes a rotation, we identify this as being a torque. So in this picture, if we exert a force on this handle, then there's a resulting rotation of this wheel. So we say that this force is producing a torque. Now, the magnitude of a torque depends on the magnitude of the force, also the direction of that force, and then finally the length of the lever arm, which I'll explain here in a moment. So the lever arm is the distance between the axis of rotation, so where the rotation is occurring about, so the point about which the rotation is occurring. So here we have the axis of rotation for this wrench. If it's turning this nut, then if the force is applied at this point here on the handle, then that distance between the axis of rotation and where the force is applied, that distance is called the lever arm. Now, the magnitude of the torque depends on the length of the lever arm, depends on the strength of the force, and then on the angle between them. So we can picture the size of the torque by drawing this lever arm trapezoid. So it's a trapezoid that has lever arm on one side, something indicating the magnitude of the force on the other side. And then the larger the area of this trapezoid, the larger the torque. So it'll probably make more sense with these two examples. So if we want to apply a large torque when you're using a wrench to turn a nut, you apply the force at the end of the wrench so that the lever arm is as long as possible, and you apply that torque perpendicular to the lever arm, so then that this resulting rectangle is as large as possible. A very inefficient way of turning a wrench would be to apply the force near the other end, so then the lever arm is short, and then also if you angle so that the torque, the force is applied almost in the same direction as the lever arm, then we have this shallow angle, and this resulting trapezoid has a small area, which means it's a small torque. Here's some other examples. So let's say that we are pushing a heavy door. Of course, the way to apply a large torque when you are pushing on a door is to push perpendicular to the door as far away as possible from the hinge. If you instead push in the middle of the door, you have a shorter lever arm, and so you don't create as much torque with the same amount of force. And if you, instead of pushing perpendicular to the door, if you push into the side of the door, down the length of the door towards the hinge, then you don't rotate the door at all. So, of course, that's not how you apply a force in order to rotate a door. Here's another example of torque creating a rotation. So when, say, a brick is tipping over, if it's at a shallow angle like this, then the lever arm would be the distance between this point of rotation to the center of gravity. The force of gravity is acting at the center of gravity for the brick. So at this point, it's a small torque because the force of gravity is pointing more or less in the same direction as the lever arm. In fact, if it pointed exactly in the direction of the lever arm, we'd have no torque, and the brick would be precariously balanced. In this case, it's a little bit off balance, and so we have a little bit of a torque causing a bit of a rotation. On the other hand, if the brick is tipped over at a greater angle, then um, we have a larger resulting torque. Even though the length of the lever arm hasn't changed, the force of gravity, which is the weight of the brick, hasn't changed, but this angle has increased, and that results in a more area of that trapezoid and more torque, and so faster rotation. Similar thing happens with a wheel rolling. So we have the lever arm being from the rim of the wheel to the center of the wheel, force of gravity acting, pulling on the center of the wheel. In this case, if it's on a constant incline, then the torque will stay constant because the wheel is round, and so this angle stays constant as the wheel is turning and rolling downhill. Now, if we think about a character and how a character will rotate by exerting a torque, here's a simple example. So Rick is going to jump into the air and turn and land facing 90 degrees to one side. So he's creating a rotation by pushing off with his feet, not just upwards, but to the sides in order to initiate a rotation while his feet are still in contact with the ground. So with one foot he pushes back one way, the other foot he pushes the other way, and then if there's a resulting torque from these forces, these are actually the reaction forces from the ground, if we have these two forces, then we have a resulting rotation, and he can twist. Here's another example, a ballet dancer doing some pirouettes. So watch when she pushes off. So here her feet are close to each other. She pushes, does a rotation. Now her feet are farther apart. She pushes, she does a much bigger rotation with her feet farther apart. And we can understand what's happening here. When your feet are farther apart, you push off with one foot. You're going to have a axis of rotation when you go on point with the other foot. The further the feet are apart, the larger the lever arm, and so the more torque you're going to get, resulting in larger rotation. It's very graceful to create the rotation when the feet are together, but it's a shorter lever arm, and so it's more difficult for the dancer to create that rotation. Another similar move is a whipped turn, which is a quick rotation with one leg in the air and the other one on the ground. So here's an example of some of those whipped turns. So you see how dancer goes down, gets a rotation going with the leg, and so if we look at that in more detail, we see the dancer has to lower her heel towards the ground, maybe not completely flat foot, but at least lower her heel to get some contact on the ground, using that contact to create a force on the ground, as we see here. So with her foot on the ground, she is starts rotating her leg. There's automatically an action-reaction force which is produced with her heel, and that creates the torque of the rotation of the leg. And then once the leg is turning, she can go on point and just use the momentum to continue that rotation. Here's a nice example of from Anchor's Way of some dancing with a lot of turns. Here's Gene Kelly doing rotations, first pushing off on the ground as he flies into the air. Jerry the Mouse is dancing with him, and here are those whipped turns where he has to keep going down on his foot in order to be able to exert torque. Finally, those turns where he's able to have his feet farther apart to get more rotation. It's best to just look at a lot of these scenes and think about what's happening with the feet and what forces have to be exerted in order to produce some torques to get those rotations. So, in summary, torque is when a force causes a rotation. Magnitude of torque depends on the direction and the magnitude of the force, and also on the length of the lever arm. The larger the lever arm, the longer it is, and just to remind you, the lever arm is the distance between the axis of rotation and where the force is applied. The larger the lever arm, the larger the resulting torque. And finally, characters can spin by creating a torque with their feet pushing off on the ground. And we saw a couple of different ways that can happen. So hopefully that gives you a sense of what rotation is all about in terms of forces, and we'll do more examples in the upcoming tutorials.